yesterday we proved that if you are given a positive real number and any natural number n, then there exists a unique number x, unique positive number x, such that x to the power n is equal to a, right. And so we can now denote this number x which satisfies this x to the power n is a, that is a is bigger than 0, and we have shown that there exists unique x bigger than 0 such that this happens. So this x we can now call nth root of a, nth root of a, and we can have the usual notation either this nth root of a or a power 1 by n. Okay, so that is about the nth roots. Now we have till now discussed what is meant by saying that a set is bounded above or bounded below or bounded, and what is meant by upper bound and least upper bound, etc. We have not discussed similar concepts about functions, but we can now do that, and the whole idea is that there is nothing really new involved here. The reason is the following: we will talk about the real valued functions. What is meant by real valued functions? That is, its range is in the real numbers, that is, or its codomain is R. Domain can be anything. Suppose A is any set and f is a function from A to R. Okay. When do we say that f is bounded? That is, this you look at this set f of A, that is a subset of R, that is a subset of R, and we already defined what is meant by saying that a set is bounded above, bounded below, and all those things. Okay. So all those things we simply apply to the function. For example, we say that f is bounded above if this set f of a is bounded above, okay, then whatever is the upper bound of f of a, we will also call it upper bound of f. Similarly, we will say f is bounded below. F is bounded will mean it is bounded above as well as below, okay, right. And in particular for the sequence, okay, if a sequence is also a function, okay, it goes from n to r. So in a similar way we will say what is meant by sequence is bounded above, bounded below, bounded, etc. Supremum of a sequence, infimum of a sequence, similarly like supremum, infimum of a function, etc. Since nothing new is involved here, we shall not spend too much time in discussing those things. Alright, what we want to discuss next is what is a broad topic: sequences and series of real number. Okay. Now before going to that, let us also make one more observation here, and that is the following. We just try to do it on this one. Show that f is bounded if and only if we can say that there exists some number, let us say m bigger than 0, there exists a number m bigger than 0 such that mod of fx less than or equal to m for every x in A. Okay. This is something very well known, fairly easy to prove, okay, and something that we shall be using very often. Okay. One way is easy. See, mod fx less than or equal to m, this is basically same as saying that minus m less than or equal to fx less than or equal to m for every x. So that means m is an upper bound, minus m is a lower bound, so that immediately shows that f is bounded. Similarly, if you assume that f is bounded, that means it is bounded above as well as below, then you can find such a number m, okay, that is fairly easy. And the same thing about the sequence, okay, if a sequence is bounded, we can similarly find a number m such that mod of xn is less than or equal to m for each n. Okay. Also, since this topic of sequences and series, etc. is something that you have already learned in your undergraduate courses, we shall not spend too much time in discussing many things in detail. We shall just quickly go through these things, basically emphasizing the role of LUB axioms in various theorems that you do. This is something you may not have realized while learning those theorems in the undergraduate course, and that is what we plan to do. Okay. So first of all, as you we already seen that xn is the sequence is nothing but a function from f function from n to r. Okay. Usually for a sequence, instead of taking the notation f, we usually take the notation x. Okay, we take the notation x. Okay, and normally we should have denoted image of this n under x as by this xn. Okay, right. This is also quite convenient notation. It is used in many books, but more customary is this x suffix n. Okay, x suffix n, and that's a sequence. Sometimes this x suffix n is also used to denote the range of the sequence. Okay, but you should in general you should not confuse between the sequence and the range. Okay, these two things are different, because the range may be even a finite set. Okay, range may even be a finite set. For example, you can take the sequence 1 minus 1 1 minus 1 etc. Okay, x1 is 1, x2 is minus 1 etc etc, but if you take the range, it is just two numbers, 1 and minus 1. Okay, all right. Let us now go to the most important definition of what is meant by saying that a sequence xn converges to a number x. Okay, so sequence xn converges, okay, is said to converge, let us say, because we are defining now, is said to converge to some x in R if for every epsilon bigger than 0, this is a well known definition, let us just recall it. If for every epsilon bigger than 0 there exists a natural number which we will call n0 in n. In general, this n0 will depend on this epsilon. Okay, so if you want, you can denote it as n0 of epsilon, but where it is understood, we did not bother about it. Okay, right, n0 in n, such that what should happen, whenever n is bigger than or equal to n0, corresponding difference between x and xn should be less than this epsilon. Okay, right, that is we can say in this way, that is n bigger than or equal to n0 implies mod xn minus x less than epsilon. Okay, okay. Now this is a definition with which you are already familiar. We will just see some implications or what exactly this means. Okay, now you already know that saying that mod xn minus x is less than epsilon, okay, that is equivalent to saying that xn belongs to, for example, this is basically equivalent to saying that xn belongs to this interval x minus epsilon to x plus epsilon. Okay, that's clear to everybody. Okay, mod xn minus x is less than epsilon, that is same as saying that minus epsilon is less than xn minus x, and that is less than epsilon, and that will give you this. Okay, right. Okay, or geometrically what does it mean, that if this is the number x, if this is the number x, and if you take epsilon, this is an interval x, so this is the length epsilon, so this will be the number x minus epsilon, x plus epsilon. Okay, then whatever epsilon you take, okay, and consider the interval x minus epsilon to x plus epsilon, except the first few elements of the sequence, that is x1 etc up to let us say xn0 minus 1, all the other elements of the sequence must lie inside this interval. Okay, that is all except a finite number of elements must lie inside that interval x minus epsilon to x plus epsilon. Okay, and whatever interval you take, okay, epsilon is just to say that you can take the interval of any size. Suppose you take the smaller interval, that is smaller epsilon, you may have to change n0 depending on that epsilon. Okay, you may have to change bigger, take maybe bigger n0. Okay, but whatever it is, okay, that number is always finite. Okay. Let me also mention a particular terminology which is used in this context. We say that something happens eventually whenever dealing with the sequence, we will say something happens eventually. Okay, eventually means this, okay, there exists some n0 such that, for example, we say that a property holds for a sequence eventually, okay, that is if there exists some n0 in n such that for all n bigger than or equal to n0 whatever we have said happens, okay. For example, here I can say that all elements of the sequence are inside the interval x minus epsilon to x plus epsilon eventually, okay. Given any epsilon, the sequence lies completely inside the interval x minus epsilon to x plus epsilon eventually. Eventually means except the first few terms, all the other terms lie inside that interval, okay. Is that clear? Okay. There are a few things which follow immediately from whatever we have said here, okay, and let us just quickly see why that happens, okay. First of all, you all know what is meant by a subsequence, okay. If you don't know, let us recall it. What is a subsequence? First of all, we take what is called a strictly increasing sequence of natural numbers, okay. That is, for example, take a sequence of natural numbers like this, n1 n1 may be equal to or bigger than or equal to 1, but n1 should be strictly less than n2, n2 should be strictly less than n3, etc., etc. Okay. As you know, such a sequence is called a strictly monotonically increasing sequence, right. Now given any sequence xn, you consider the sequence xn1, xn2, xn3, etc., okay. That is, you are taking some terms from the given sequence, okay, but not arbitrary terms. You first fix a sequence, strictly increasing sequence of natural numbers, and take the corresponding sequence of corresponding terms of the given sequence, then this is called subsequence of xn, okay, subsequence of xn. For example, if I write a sequence like this, x2, x1, etc., this is not a subsequence. Is that clear? Why this is not a subsequence? Because we have taken n1 as 2 and n2 as 1, okay, right. So you cannot change the order in which the elements occur in the sequence. You have to retain the same order and then pick up some elements from there. That is important. Okay. Now where do subsequences come into picture here? If a sequence converges to a number x, all its subsequences should also converge to the same element x, okay. So that is the first theorem we will say. If xn converges to x, then all subsequences of xn converge to x. Okay. Well, how does this follow? We can say that we already know that xn converges to x. That means we know that given any epsilon, there exists n0 in n, such that either you can say it this way or this way, mod xn minus x is less than epsilon for all n bigger than or equal to n0. Now this suppose you take this whatever nj, let us say, if nj is bigger than n0, bigger than or equal to n0, then for all elements of this sequence, which are for all indices which are bigger than or equal to that nj, those xnj also will lie in this mod in the same interval, okay. After all, xnj's are coming from these xn's, so if something happens for all xn for n bigger than or equal to n0, it should also happen for all xnj for nj bigger than or equal to n0, right. So there is nothing really great that is happening here, okay. But what can happen is that the original sequence may not be convergent, but it may have many convergent subsequences. For example, here, okay, we will see that, okay, let us since we have come to this point, let us again let us go back to this. Okay, in general, how does one show that a sequence converges? Of course, till now we have only seen this definition. Okay, so as of now we can only use the definition and to show that a sequence converges. Subsequently, we shall see many other methods. Okay, we will use some of the well-known theorems to show that some sequence converges. But using this definition, what we can show, for example, suppose you take a constant sequence. Let us say, let us take some examples here. Yeah, by the way, the proof of this is clear, so I need not discuss it here. Okay, I have mentioned. You can write the proof on your own. Okay? So take an example. Let us say constant sequence xn equal to 1 for all n. Okay. When you have to show that limit of a, yeah, by the way, I didn't mention that this xn converges to x. Okay, this is invert, xn converges to x. There are a few other notations used for this. One is this, we also say that xn then right arrow x as again n right arrow infinity. Okay, we say that xn right arrow is read as tends to. Okay, xn tends to x as n tends to infinity. Okay, that is a symbol used, and there is another notation for this, limit of xn as n tends to infinity is equal to x. Okay, you are all familiar with this. All these three things mean the same thing. Okay, it is just a different way of saying the same thing. Certain things are convenient to use at different times. Okay, for example, in olden days, when you needed to type things, this was a more convenient way to write because those arrows and all were not available. But now those kinds of things are, those kinds of problems are not there. Okay. Anyway, so suppose this is a sequence. For this sequence, you can say first of all, to show that a sequence converges, you have to have some idea of what this number x is. Okay, because sequence, a given sequence xn has to converge to some real number. Okay, which we call limit of that sequence xn. So you have to first of all have some idea of what that limit is. Okay, then only you can think of showing that a sequence converges to that that limit. Okay, now in this particular case, what it is clear that the limit has to be 1. Okay, each element xn is 1, and so suppose I want to apply this definition, then you can say that given any epsilon, you have to take x equal to 1 and mod xn minus x is 0 only. Okay, for all n. Okay, so this is trivial. Okay, there is nothing. So every constant this is a constant sequence. Even if you take some other constant here, that's not going to change. So every constant sequence converges, right? Okay. Let us take one more example, which is again very popular and which we shall be using very often. I mean that sequence and certain other sequences depending on that. For example, you take now xn is equal to 1 by n. Okay. Now to show that this sequence, okay, first of all, I believe all of you know that this sequence converges. Okay, and it converges to 0. Okay, so the whole question is how does one show this and what is actually involved in showing that. Okay, okay. So in this case we have to take x is equal to 0. Okay, so this xn converges to this x 0. Now to do that, what we will have to show, we will have to look at mod xn minus x. Okay, so mod xn minus x, that is the thing but mod 1 minus n minus 0, and that is the thing but 1 by n, right, whatever be n. Okay, so now what is the idea, given epsilon, we should find an n0 such that for n bigger than or equal to n0. Okay, let us say what is that is to show this, for every epsilon bigger than 0 there exists n0 in n such that for all n bigger than, there is n bigger than or equal to n0 implies 1 by n less than epsilon. Okay, right, 1 by n less than epsilon. Okay, now you can see that saying that this 1 by n less than epsilon, that means n greater than 1 by epsilon. Okay, right. Okay, now if you find n0 which is bigger than 1 by epsilon, okay, if you find one n0 which is bigger than 1 by epsilon, then whenever n is bigger than or equal to n0, that n is going to be bigger than 1 by epsilon. Okay, so what is the issue now? Just to find n0 which is bigger than 1 by epsilon, or to show that there exists n0, whatever epsilon is given, to show that there exists n0 which is bigger than 1 by epsilon. Okay. Now does such an n0 exist? Okay, fine. How does that follow? Right, that is what we have. Okay. We have shown that n is not bounded above. So whatever epsilon is given, 1 by epsilon is a positive real number, we can always find some natural number bigger than that because n is not bounded above. Okay. So why I went through so many details of this particular example, it is that to show that 1 by n converges to 0, all that is something which you have realized, which you have thought to be very obvious all these days. The idea is that the proof that 1 by n tends to 0 involves the idea that n is not bounded above, and that involves the LUB axiom. Okay. If you remember, in order to show that n is not bounded above, we have used LUB axiom. Okay. So to show that 1 by n tends to 0 basically involves LUB axiom of the real number system. Okay. Alright. So that is about showing that a sequence is convergent. Okay. Suppose you want to show that the sequence is not convergent. For example, you know that this sequence is not convergent. Okay. Now that is usually more difficult. Okay. That is usually more difficult to do. Let us first see how one can attempt to show it by using this definition. Okay. Right. We shall see easier methods little later. Okay. Suppose you want to just use this definition, then by this definition saying that a sequence does not converge means what? It means no such real number exists, right? No such real number exists. Okay. It means what? Whatever x you take, okay, whatever x you take, for that x such a thing is not going to happen. Okay. What does it mean? See, here you say that for every epsilon something happens. Okay. Okay. If for every epsilon something happens, if that is false, means there exists some epsilon for which it does not happen. Okay. What does not happen? That is there exists n0 such that for all n bigger than or equal to n0, mod xn minus x is strictly less than epsilon. If this is false, that means what? For whatever n0 you take, you can always find some n bigger than or equal to that n0 such that mod xn minus x is greater than epsilon. Okay. Right. Now this is something very useful, and this is something that you should maybe record somewhere. Okay. To show that a sequence is not convergent using only the definition. Okay. To show that a sequence is not convergent, what is needed to be shown? To show sequence is not convergent, so is not convergent. What we need to show is that for every x in R, okay. See, there are two things here. Okay. Suppose you wanted to show that a sequence xn does not converge to x, okay, then we need not take for every x in R. Okay. Alright. But now we just want to say sequence xn is not convergent. We can, so what we have to say, for every x in R there exists some epsilon, let me call it epsilon suffix 0 because it is, we have used this notation for general epsilon. There exists, in fact that epsilon may depend on x. Okay. That epsilon may depend on x. There is such that for all n0 in n, that is whatever n0 in n, there exists n bigger than or equal to n0 such that mod xn minus x is bigger than epsilon, bigger than or bigger than or equal to epsilon 0. Okay. 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 So this is something you should always remember, that if you want to show that a sequence is not convergent by using definition, this is what you need to show. Okay. This is what you need to show. We shall see easier methods little later. Okay. Okay. Now coming back to this sequence, suppose I want to show that this sequence is not convergent using that. Okay. Right. Then I should show that whatever x is there will exist some epsilon. Okay. Can you tell me some obvious choice for this epsilon here?
1 by 2.
Yeah, for example you can take 1 by 2. Now why we say this, the reason is the following. Okay. Saying that a sequence xn converges to x, if you look at this definition, geometrically it means that all the terms of the sequence go close to x. Okay. roughly speaking it means this, that is given epsilon, for every epsilon mod xn minus x there exists n0 such that for all n bigger than or equal to n0 mod xn minus x less than epsilon means after n0 all terms of xn are close to x. Okay. Now if all terms are close to x, it means the question is, can there exist some x such that 1 is also close to x and minus 1 is also close to x. Okay. Okay. Now that obviously cannot happen because for example as somebody said, suppose I take epsilon be equal to half, suppose I take let us say take epsilon 0 equal to half. Okay. 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 Then whatever x you take, what must happen is that suppose here, okay, to take the interval if epsilon 0 equal to half, this is x minus half, that is x plus half. Okay, this is x minus half and that is x plus half. Okay. Then what we if this sequence xn converges to this x, if the sequence, then all terms of that sequence must lie in the interval x minus half to x plus half. Okay, right. Okay, but whatever n0 you take, you can always find some n such that xn is 1. Similarly, you can always find some n such that xn is minus 1. Okay, if xn is 1, xn plus 1 will be minus 1, and both of them have to lie in this interval. So minus 1 and 1, both of them must belong to this interval. Okay. Now can that happen? Okay, because the length of this interval is 1. Okay, if minus 1 and both of them have to belong, then obviously that length will be bigger. Okay, so this sequence does not converge. Okay, but of course you will see that this is it will be very difficult to prove this kind of thing for every non-convergent sequence. Okay, so proving that a sequence is convergent or not convergent using definition alone can be quite a difficult task. Okay, and that is why we shall see some easier methods to show both of these things. Okay, when a sequence converges and similarly when a sequence does not converge. Okay. Okay, now let me come to the first method. Now look, that is where this theorem is very important. Okay, here what we have proved, that if a sequence xn, yeah, by the way before that let me also mention here. Okay, so this is if we want to say that a sequence xn does not converge. Okay, suppose I simply want to say that sequence xn does not converge to a number x. Okay, then as I said earlier, then this for every x that will go. Okay, we have to simply show that there exists epsilon 0 bigger than 0 such that whatever I have written after that happens. Okay, that is for that particular epsilon 0, for every n0 you can find some n bigger than or equal to n0 such that mod xn minus x is bigger than or equal to epsilon 0. Okay, right. Okay. Okay. Now look at this theorem. Here what we have showed, that if xn converges to x, then all the subsequences of xn should also converge to that same number x. Okay, all right. Now before going to that comment which I have in mind, let me also mention one more thing, again a well known theorem, that if a sequence converges, okay, it has to converge, its limit is unique. Okay, a sequence cannot converge to two different limits. Okay, so let me simply say this, limit of a convergent sequence is unique. Okay, all right. Now how does one show that something is unique? You assume that the sequence converges to two different limits and get a contradiction, right? So suppose xn converges to two different limits. Okay, suppose limit n tends to infinity. Okay, so let me use that notation. Suppose xn converges to x and xn converges to y. Okay, now if x is different from y, right, x is, so we can assume that x is less than y. Okay, we can assume that x is less than y. I think I will just explain the proof geometrically, you can write the proof. Okay, suppose this is the case, x is less than y. Okay, all right. Now can we find an epsilon? I think it is better to look at this way of defining. Can we find an epsilon such that the interval x minus epsilon to x plus epsilon and y minus epsilon to y plus epsilon are disjoint? That is possible. What is the obvious way of choosing that? Yeah, you take any number which is such that 2 epsilon, see this is the length epsilon, that is the length, so the total length will be 2 epsilon. You choose any epsilon such that 2 epsilon is less than y minus x. Okay. In general, we can choose any epsilon satisfying this 0 less than epsilon less than mod x minus y by 2. Okay. That will take care of both the cases, x less than y or y less than x, right. Now, since xn converges to x, okay, I will just tell you can find some n, you can find let us say some n1, let me take such that for n bigger than or equal to n1 all of these xn's lie in this interval. Okay. Since xn also converges to y, you can find some let us say n2 such that whenever n is bigger than or equal to n2 all those xn lie in this interval. Okay. Right. Now but you can always find n which is bigger than or equal to both n1 and n2. Okay. Right. You can always find n which is bigger than or equal to both n1 as well as n2, then for that n xn should lie here also and here also, right. That is not possible, right. Okay. Right. Okay. So that shows that a limit, if a sequence may or may not converge, but it certainly cannot converge to more than one number. Okay. Whenever it converges, its limit is unique. Okay. All right. Now let us come back to this theorem. Okay. Here we have proved that if xn converges to x, all the subsequences of xn should also converge to that same limit x. Okay. Now suppose you find a sequence and suppose that sequence has let us say 2 subsequences. Okay. Okay. One subsequence converges to one number and the second subsequences converge to some different number. Then what can you conclude from that? Obviously sequence, because we have shown that if a sequence converges all its subsequences must converge to that same limit. Okay. So obviously if the 2 subsequences converge to 2 different numbers then the sequence cannot be convergent, right. Now does that give an easier method to show that a sequence does not converge? Right. For example, look at this sequence, okay, right. Take x1, x3, x5 etc. Okay, right. That is a constant sequence 1. So here you have a subsequence which converges to 1. Okay. Then take x2, x4, x6 etc. That is also a subsequence, that is a constant sequence minus 1, right. Okay. So that constant sequence converges to minus 1. So you have 2 subsequences converging to 2 different numbers. Okay. So from that we can conclude that the sequence does not converge, right. So that is an easier way of showing that a sequence does not converge, right. Okay. Now one more property of convergent sequence, every convergent sequence is bounded. Every convergent sequence is bounded. Okay. Okay. Again that is straightforward, nothing much to be needed there, because how does to show that a sequence is bounded, you need to show that it is bounded above and bounded below, or you can show that there exists some m such that mod xn is less than or equal to m for all. We can choose any way. Okay. Look, suppose we take some epsilon bigger than 0, okay. We can take any epsilon, it does not matter. Okay. You can take for example epsilon equal to 1. Okay. Then we know that for that epsilon there exists some n0, okay, such that all xn bigger than or equal to n0, for all n bigger than or equal to 0 xn must lie in this. Okay. Xn must lie in this means what? It means xn is less than x plus epsilon for all n bigger than or equal to n0. Okay. Right. Okay. Now what are the elements that are left out for which this may not be true? x1 to xn0, x4, they are finite numbers, there are finite minimum. You take those, how many are there? There are n0 minus 1. Okay. You take those numbers plus this number x plus epsilon, okay, and take the maximum of all of them. Okay. Let us say suppose that maximum I call alpha, alpha is maximum of what is that x let us say xn or let me say x1 x2 etc. up to xn0 minus 1 and x plus epsilon, okay. Then I can say that that xn is less than or equal to alpha for all n, right, okay. So xn is bounded above, okay, this is an upper bound, okay. Similarly we can say it is bounded below, okay, you can take minimum of x minus epsilon and these numbers, that will be a lower bound, okay. So every convergent sequence is bounded, okay. So this tells you one more way of showing that a sequence is not convergent, okay, right. For example, suppose you take a sequence, suppose the sequence xn, let us say xn is equal to n, okay, then obviously this sequence is not bounded and hence not convergent, okay. So whenever you learn a property of a convergent sequence, if that property does not hold, it will mean that the sequence is not convergent, okay. Now let us recall some of the well known theorems about the limits of sequences, and as I said, since those are the things with which you are already familiar, we will not go through those proofs in very much detail, okay. First of all, we want to discuss how the various algebraic properties of real numbers are related to this concept of limit of a sequence, okay. In other words, what we want to say is that suppose xn converges to x and yn converges to y, okay, then what can we say about the sequence xn plus yn, xn into yn, etc., okay. So let me just write that, okay, suppose xn converges to x and yn converges to y, okay, then we want to say so many things, so I will just write here, okay. Then first of all we say that xn plus yn, this sequence converges to x plus y, okay. And you would have seen the proof of this several times, I will just quickly recall this, and all other things I will state without proof, okay. To show that xn plus yn converges to x plus y, we use the standard definition. So suppose we take some epsilon bigger than 0, okay, then for this epsilon we have to find some n0 such that whenever n is bigger than or equal to n0, mod xn plus yn minus x plus y, that is less than epsilon, okay. Now all that one has to notice here is the following, that is if you look at mod xn plus yn minus x plus y, that is nothing but xn minus x plus yn minus y, and because of the properties of the absolute values which we have seen, so this is less than or equal to mod xn minus x plus mod yn minus y, okay, right, okay. And then we know that xn converges to x and yn converges to y, so we can choose n0 or n1 or etc. sufficiently large so that each of these can become less than epsilon by 2, okay, right. This is called a standard epsilon by 2 proof or 2 epsilon proofs or whatever you call, okay. The idea is that to make each of these things sufficiently small so that the sum becomes less than epsilon, okay. So we can say that first of all we can say that since xn converges to x, there exists n0 in n, or let me call it n1, okay, n1 in n, such that n bigger than or equal to n1 implies mod xn minus x less than epsilon by 2, okay, alright. And Similarly, since yn converges to y, I can say there exists n2 in n such that n bigger than or equal to n2 implies mod yn minus y less than epsilon by 2, okay. And we can say that take the maximum of n1 and n2 and call that number n0, okay. So let n0 be maximum of n1 and n2, okay. Then for n bigger than or equal to n0 we can look at this, okay. Xn plus yn minus x plus y, that is less than or equal to mod xn minus x plus mod yn minus y, and each of this is less than epsilon by 2, okay. So this whole thing is less than epsilon by 2 plus epsilon by 2, that is epsilon, okay, right, okay. Remember the whole thing is that for large values of n, xn is close to x, yn is close to y, and hence xn plus yn must be close to x plus y. That is what we have been using and we have been proving, okay. There is nothing very particular about this epsilon by 2 here, okay. You could have taken this as epsilon by 3, that as 2 epsilon by 3, epsilon by 4 or 3 epsilon by 4, whatever, okay, it does not matter, okay. Epsilon by 2 is just convenient, okay. Alright. In a similar way you can prove that if you take any real number k, okay, then k times xn converges to kx, okay. Only thing is in this proof you will have to make two cases. If k is equal to 0, this becomes a constant sequence xn, then there is nothing much to do there. If k is not 0, you look at mod of k xn minus kx, okay. And so if mod x, so instead of epsilon by 2 here you take n0 such that mod xn minus x is less than epsilon by mod k, okay, right, and then k xn minus kx, mod of that will be less than epsilon, okay, that is trivial, okay. Similarly now for the product you have to do little more work, okay. Xn into yn converges to xy, okay. Again this also this proof I will not discuss here, you would have seen this and you can try to reconstruct on your own. For that you will have to use this property that every convergent sequence is bounded, okay, right, okay. Then little more involved is the proof when you look at instead of xn yn, if you look at xn divided by yn. First of all for that you have to assume that yn is not 0, okay, and also we expect to show that it is converges to x divided by y, so y also should not be 0, okay, okay. So let us so that assume yn is different from 0 for all n and y is different from 0. Remember simply saying that yn is different from 0 for all n does not ensure that y is not 0, okay. It can happen that every term of the sequence is non-zero but a limit can be 0, okay. We have seen that example 1 by n, okay, right. So then xn by yn converges to x by y, okay. So this is about the algebraic properties, how the limit of a sequence behaves with respect to various algebraic properties of the real number system. We also want to say something about the order properties. Now what is meant by order properties? That is, suppose we know that xn is less than or equal to yn for all n, okay. Can we say something about the limit? Okay. We need to expect it x less than or equal to y, okay. So if xn is less than or equal to yn for all n, then x is less than or equal to y, okay. okay. Again it is fairly easy to prove this, okay, because if x less than or if that is false means what, y is strictly less than x, okay. You can easily find some epsilon such that x minus epsilon is bigger than y, okay. That is, suppose this is false, it means let us say this is x is strictly bigger than y, okay, x is strictly bigger than y, okay, right. Then you can easily find some epsilon such that this interval y minus epsilon to y plus epsilon is like this, and this interval x minus epsilon to x plus epsilon is like this, okay. Then find the corresponding n0, n1 or whatever, etc. So for large n, xn is going to lie between x minus epsilon to x plus epsilon, and yn will lie between y minus epsilon to y plus epsilon. So you can find some value of n such that yn is in this interval and xn is in this interval. Now that is not possible, right, because we assume that xn is less than or equal to yn, okay. Only thing that you should remember here is that even if this inequality is strict here, even if xn is strictly less than yn for all n, we cannot say that x is less than y, okay, right. If xn is less than or equal to yn for all n, we can conclude from that x is less than or equal to y, but xn strictly less than yn does not imply that x is strictly less than y, okay. Can you again give me an obvious example of this?
By n square.
You can take the sequence 1 by n and take the constant sequence 0, okay. Suppose you take xn as constant sequence 0, yn as 1 by n, then xn is strictly less than yn for all n, but x is not less than y, right, okay. Okay. Now there is one more very interesting thing that depends on this order property, and normally that is, suppose you take 3 sequences xn, yn and zn, okay, such that suppose there exists a sequence zn, suppose there exists a sequence zn such that let us say this zn lies between xn and yn for each n, such that xn, okay, whichever way we say that xn is less than or equal to yn less than or equal to zn, xn is less than or equal to yn less than or equal to zn, okay. And suppose xn converges, zn also converges, and suppose both of them converge to the same limit, okay, okay. Suppose limit of xn as n tends to infinity is same as limit of zn as n tends to infinity. Remember, this symbol is to be read as limit exists and equal to some whatever number is there, okay, okay. Suppose this common limit is what I call, let us say, L, that is xn converges to L, zn also converges to L, and for each n, okay, this should be true for all n, for each n xn is less than or equal to yn less than or equal to zn, okay. Then what should happen, that this yn also converges and it converges to the same limit, okay. Then limit by n as n tends to infinity is also L, okay. In fact, this theorem is very well known. It is called sandwich. This last part, this is called sandwich theorem, okay, right. I mean, the idea is that the sequence yn, it's sandwiched between the two convergent sequences, then that should also converge, okay, and should also converge to the same limit, okay. And these are the theorems. See, till now we have, to show that a sequence is convergent and to get the limits of the sequence, these are the theorems which are used very often, okay. That is, till now, for example, we have seen the limits of only 2 sequences, okay. One is the constant sequence and other is the sequence 1 by n, okay. But now using these theorems, one can decide the convergence or divergence of various sequences and also decide what their limits is. For example, something like this, let us say 3n plus 5, suppose xn is something like 3n plus 5 divided by 7n minus 1, okay, right. Then you know that what is done in this case, you write this same thing as n plus 5 by 7 divided by n minus 1 by 7, okay. Oh sorry, not this way, divide everything by 1, this is 3 plus 5 by n and 7 minus 1 by n, okay, right. And then what are the theorems that are used to show that this sequence is convergent? First of all, we have shown that 1 by n is convergent sequence, that goes to 0, okay. So 7 minus 1 by n, that goes to 7, there we are using this fact, okay, xn, okay. Then 5 by n, that should also goes to 0 using this, okay, right. And then 3 plus 5 by n, that should go to 3, again using this first part xn plus by n, okay. And finally the limit of this is 3 by 7, that follows by using this, okay, because using this, because here yn is not 0 for any n and its limit is also not 0, so xn by n converges to x by y. So using all these things we can conclude that this sequence converges to 3 by 7. This is something you have been doing all along, but perhaps not realizing that in concluding that this sequence converges to 3 by 7, you have basically used all these things, okay, right. We can similarly see the illustrations of this. In fact, this last thing, sandwich theorem, is also very useful in showing that certain sequence is convergent. For example, one of the ways of showing that a sequence is convergent is that you find two sequences, one smaller than or equal to that and one bigger than or equal to that, such that, and show that those two sequences converge to the same limit, okay, and conclude from that the sequence by n also is convergent and goes to the same limit. This is a very standard technique in showing that a sequence converges, okay. We shall see some examples of that in the next class.